All right, everybody. Today we're going to take a look at exponential functions. And just a quick reminder here, please do your homework in pencil. Don't use pen. You're going to make mistakes. You have to cross it out. Just get in the habit of using a pencil. Thanks. All right, this goes for a lot of the lectures. Some of it's from the book, some of it is not. And even if it is from the book, I try to kind of take it and condense it down. So taking notes is really key. Well, if you're watching this video right now, you know that these videos are available online. You can always come back here and take another look at the material. All right, here's the calculator we use in class, the TI Nspire CX-CAS. You can also use the 89. There are lectures available online on Mr. Kelly's website if you wanted to see those. But I think most of us now have the Nspire, so that's what everything is going to be geared towards. So go ahead and take out your calculator if you don't have it, because a lot of this lesson is going to require it. Turn on your calculator and press the scratch pad key. And that's how we toggle between graphing and calculating. All right, this isn't really a formula that we need to have memorized for this class, but it's a good one for us to introduce some of these ideas of exponentials and to get used to our calculator. So compound interest, this is our formula right here, the final amount, a principal amount, that's how much you start with, your rate, how long you're getting interest, and the number of times it's compounded per year. So if it's compounded yearly, n would equal 1, compounded monthly, n would equal 12, and so on. So let's just take a look at how this works. If we have $100 invested for 4 years, 5.5% interest compounded annually. So thinking back to that formula from before, we have 1 plus 0.055 divided by 1, because our number of times compounded per year is 1. We plug that into the formula, we can crunch those numbers and get 123.88. So you started with $100. After 4 years, you had $123.88. On the Nspire, you would type in 100 times 1.055 to the power of 4. So see if you can find all of those keys. In general, an exponential function is of the form a to the power of x. All right, we're going to look at graphing. We can graph y equals a to the power of x for different values of a. We're going to do this in a window with x values going from -5 to 5, y values from -2 to 5. So press that scratch pad button, that'll take you to a graphing screen. If you're not already in the function line, press tab and input 2 to the power of x. Enter, and you'll see the graph for 2 to the power of x. And if we want to put in multiple functions at a time, we can do that. Press tab. So we press tab again, input 3 to the power of x into the second function line. And you could press enter and then press tab again, or you could just press down and you'll go to the next function line. Input 5 to the power of x. Now, after you've pressed enter, you can see all 3 functions at the same time. And now to change the dimensions of the viewing window, press menu, scroll down. You can press 4, window zoom, and press enter. And by the way, yours might not be 4, depending on if you have a different version of the Nspire. It might be 5 or 6. Just look for the window zoom and go to that function. Window settings, and you're going to input the values you want for the window settings. So the minimum value of x, -5, max is +5, y minimum -2, y max +5. Make sure that you use the negative button, not the minus button. There's a difference between the two. The negative on the key has these parentheses. Press enter. And now you can see that the window looks much nicer than it did before. So we can think about this. We have 2 to the power of x, that's the function in blue, 3 to the x is in red, 5 to the x is in black. Where is 2 to the x less than 3 to the x less than 5 to the x? And that's everywhere from x equals 0 to infinity. And where are they bigger, you can see that when x equals 0, they switch, so from -infinity to 0. And they're equal right there at x equals 0. The domain, negative infinity to infinity, meaning you can plug in any value of x that you want. And the range goes from 0 to infinity. So these functions get closer and closer to 0, but never quite get there. Okay, population growth is an area where we often see exponential growth. So we can see the world population for these years from 1986 to 1991, and we can find the ratio between those. By dividing one year by the previous year, we find that the rate of growth is approximately 1.018. We can see that it's not exactly the same every year, but pretty close. So the population would be 5,000 or 5,422, that's the population in 1991, times the rate of growth, 1.018, to the power of 19. And that's so we can find the population in the year 2010, because it's 19 years from 1991. We would find that we would have expected the population in 2010 to be 7,609. Radioactive decay can also be modeled with an exponential function. And this would actually be exponential decay because the amount is going down. Start with 5 grams of radioactive substance, has a half-life of 20 days, meaning every 20 days you have half of what you started with. We want to know when there will be 1 gram left. So after 20 days, half of 5 is 5 halves, or 2.5. After 40 days, we have half of 5 halves. That's 5 fourths, 1.25. For t days, it's 5 times 1 half to the power of t over 20. Because look back at those previous equations. The first one, after 20 days, 5 times 1 half to the power of 1. 1 is 20 divided by 20. After 40 days, it's to the power of 2. That's 40 divided by 20. So take whatever number of days t divided by 20. Now we can solve this using logs. We did that last year, but we're going to show you some of the capabilities of our calculators. So go ahead and clear the previous graph. You can go through Menu, Actions, Delete All, Enter. Or if you, our shortcut really is Doc B, and that clears everything on your calculator. Anything you've input on the graph screen, anything on the calculator screen, if you don't need it anymore, just press Doc B and you'll reset everything right to the beginning. So go back to the graph screen. Okay, type in 5 times 1 half to the power of x over 20. Now you can type this in using division, you can type it in using the actual fraction button. Press enter. We're going to change our window settings, x 0 to 60, y from 0 to 5. Enter, and we can see what this looks like. Now notice, we have 2 functions here. We have the function for our substance that's decaying. That's 5 times 1 half to the power of x over 20. We also graphed f of x equals 1 because we want to know when the amount of substance is 1. In other words, when is y equal to 1? So now we just have to find the intersection of those 2 lines. If we go to Analyze Graph under Menu, Intersection, it's going to bring up this dotted line. And you're going to use your the touchpad in the middle of the screen to move that line around to one side or the other of the intersection. And you can press the middle button or you can press Enter to drop down that dotted line. And then you can slide over to the other side of the intersection, drop down the other dotted line. You're telling the calculator to find the intersection between those 2 dotted lines. Now it's a little bit hard to read this. We can actually fix that. Hover over the number, press the plus button to change the number of digits, press Enter, so we can make it so we get a little more accuracy. And if you hover over the functions or the intersection point, you can press Control and then that middle button there to grab it, and you can move things around the screen. And you can see now we have it in a way that's much easier to read than before. And then some other things we can do that you probably won't need to, but it's just fun to, it's nice to know that you can do it. You can change the color, Control, Menu, Color, and you can change the color of the lines. Now, I'll show you another way we could have solved this without graphing. So press that open book, that's our catalog, and it gives us every capability of the calculator right there. We're going to look for solve. You can press S to skip over everything, get you down to S, then scroll down to solve. And look at the bottom here, it says solve parentheses equation comma var. And that tells you exactly how the calculator is expecting you to input your information. Type the equation. Remember that equation must have an equal sign, and then the variable that you're trying to solve for. Okay, press enter. Type in 5 times 1/2 to the power of x over 20. And then followed by comma, or equals 1, comma x. So we're solving that equation, trying to find out when there's 1 gram of substance left, and the variable we're trying to figure out that tells us that would be x. Press enter, and the calculator will do that work for you. Notice it gives us the answer in the exact form. If you want a decimal approximation, arrow up to highlight that answer, press enter to bring it down, and then control enter, and the calculator will give you a decimal. So for continuous compounded interest, that's a equals p times e to the power of rt. So e 2.718 on, and we'll actually look later in the year at how we where that number comes from. For now, we'll just use it. Here's kind of a glimpse into where it comes from. We have the function 1 plus 1 over x to the power of x. As x gets really, really big, the value of that function approaches e. And you could test that out by plugging in x equals 100 or 1,000, and you'll see that it's a value really close to 2.718. So we can graph that. We can trace, menu, trace, enter. Gives you this little circle with an x through it, and you can slide that along the curve. We could also construct a table. Menu, table, enter. And we can investigate using the table. We can edit the settings. We can go by 1,000s. This allows us to see what happens when x gets really big. And you can see very quickly it gets towards 2.718. If you want to get rid of the table, menu, table, remove, or you can also press Dock B, and that would just clear out everything.